You want to separate them with an insulator that has a very low dielectric constant, and therefore is a huge drive to create such things of this sort going on right now. There's also a property called the loss tangent, which has to do with the energy dissipation from alternating currents and such things. I'm not going to talk about that. I'll just mention in passing that such a thing exists. Breakdown voltage. When you get a lightning bolt through an insulator. This, by the way, can be a huge issue. We have in California, and I've done a couple of failure analysis that involve these over the years. You're walking down the sidewalk, and you notice a manhole cover. Very often what's under that manhole cover is a transformer. And occasionally those transformers, you get a little water in there or something, and they kind of age and they corrode, and they go boom. And every now and then someone is standing on top of the manhole cover when it goes boom. And then that result can be very serious injuries and lawsuits and all that kind of thing. It happens. The insulator protects again until the electric field reaches the critical value, at which point you get essentially a bolt of lightning, a catastrophic increase in current at the value AC. If I plot the current in an insulator as a function of field, it is effectively zero until we get very close to the critical current, and at the critical current it jumps to a very, very high value, and that's your lightning bolt essentially. The common way that you get electric breakdown, a number of material defects can lead to electric breakdown, but let's stay superficial. So I'm only going to tell you about the most common cause, the most fundamental cause of electric breakdown, dielectric breakdown, and that's the following. Even if you have a big band gap, and even if you're at a relatively low temperature, there are an awful lot of valence electrons down here, and at least a few of them are going to get excited into the conduction band, even if this band gap is significant and the temperature is low. Once these electrons get into the conduction band, if there is an electric field, they're going to be accelerated in that electric field. Now, since there are no other electrons up here in the conduction band, or very few, they can be accelerated very efficiently. If this electron gets accelerated to a high enough velocity, and it runs into an atom, for example, due to a fluctuation through a thermal vibration, then it can have sufficient velocity that it ionizes an electron from that atom. We get excitation not thermally, but mechanically, if you want, with our accelerated electron running into the ion core of some ion and ejecting an electron from it. So when we get the field to some critical value, this process can take off. Ordinarily, these ionization processes would be sufficiently infrequent that you get back to equilibrium, no real problem. But suppose I get a high enough field that this process becomes frequent enough that it cascades. This electron hits an ion core, produces 2 electrons, they get ion cores, produce 4 electrons, 8, 16, in no time at all, you've got 100 billion electrons, and you've got a lightning bolt. Yeah. I'm sorry? Electrocution. Electrocution, you just run a big enough current through somebody to paralyze their internal organs. Now, you don't really use a lightning bolt in electrocution. You need surprisingly little current to electrocute a human being, unfortunately. That's why people electrocute in their bathtubs by touching wires and such things. Don't assume you need much current to kill yourself. Unfortunately, you don't. I do not suggest that you try. The lightning, this is huge. This is really big. And it happens generally because of this cascade process. One of the interesting things about the cascade process is that the critical current well, obviously your critical current is going to depend on things like defects in the solid, because these defects are activation sites that can give rise to carriers. So the more defects you have, the sooner you're going to develop your carrier concentration and the lower the critical voltage is going to be. The critical voltage also, interestingly, and even an ideal insulator, reaches a minimum value. The critical voltage reaches a minimum value at some intermediate temperature. And the reason is that when the temperature is really very low, you have almost no carriers. So no matter how big the voltage is, it's kind of hard to get enough carriers going to trigger breakdown. You can do it, but it's very hard. If you get to very high temperature, you will get more carriers, although in an insulator you're still not going to get all that many. But now the mobility of those carriers is very low because the temperature is so high. So they don't get accelerated enough to trigger the cascade unless you've got a big critical voltage. So at low temperature, the critical voltage is high. At high temperature, the critical voltage is relatively high. There's some intermediate temperature at which it reaches a minimum value, and that's the reason. Of course, purity, EC, will increase the purer you make your material, and of course it also increases the bigger your band gap is.
What range of temperatures we consider intermediate?
Depends on the insulator. Unfortunately, it can be around room temperature for a number of insulators, but it's very sensitive to the temperature of the band gap you're talking about and so on. The behavior of a dielectric in supporting an electric field. The easiest way to understand that, which you should have seen before in one of your physics courses or one of your other introductory courses, is just to look at a simple capacitor. A capacitor is a couple of parallel plates on which we deposit a charge, and let's assume the space between them is a dielectric, even if it's the vacuum state functions as a dielectric. The relation between the charge and the voltage drop across a capacitor, is given by the classical electrical engineering formula. The charge is capacitance multiplied by voltage. Voltage is the voltage drop between the two plates. As with most other things like Ohm's law, this is not a convenient formulation for materials people because it confuses material properties and geometry. So the first thing we have to do is get the geometry out of this equation. Well, the charge on a plate is equal to sigma, the charge density, multiplied by A, the area of the plate. The voltage is the electric field, assuming it's constant, multiplied by the distance between the two plates. So if I gather the geometric constant on this side, I can get that sigma is the electric displacement. This is an equation you'll see in fundamental physics, is proportional to the electric field. And in modern terminology, depending on which textbook you pick up, you'll see this equation written differently. But in modern terminology, that's the product. The coefficient is the product of two parameters. One, epsilon 0, is the dielectric constant of free space, and the other epsilon is the dielectric constant. And we write the equation in this way so that the dielectric constant is a simple number. It's the ratio between the dielectric effect in the material and the dielectric effect in free space, and this number must be greater than or equal to 1. And it's a simple number, 1, 2, 1.5, something like that. So it turns out to be a simple number. It's also a dimensionless number, which can be very useful. The dielectric constant then relates the field to the charge density. We often use not the dielectric constant, but the susceptibility, chi, which is epsilon minus 1. Chi is equal to 0 in free space when epsilon is equal to 1. Why do we have a dielectric constant? The dielectric constant comes from the polarization of polarizable media within the material. Suppose, for the sake of argument, we have a medium here that contains dipoles. And suppose we now put charges on the two surfaces. Positive charge here on the bottom, a negative charge here on the top. Well, and I'm much more interested in you understanding the physics than the mathematics over here. What's going to happen? The positive end of those dipoles is going to be attracted to the negative charge. The negative end of those dipoles is going to be attracted to the positive charge. That means that these dipoles are going to tend to align. When they align themselves, they create an internal field. Here's negative, here's positive. They create an internal field that opposes the applied field. As a consequence, the actual field inside the dielectric is less than you would think it would be just based on these two charges. And in fact, d sigma, turns out to be the sum of the applied field, written as epsilon 0 E, plus the polarization field, which we write as P. That says the dielectric field is 1 plus P, which is the polarization, sum of all the dipole moments, divided by epsilon 0 E. The thing I want you to learn from that, you certainly don't need to memorize this formula, but to recognize that we're getting dielectric behavior. Because if we have any polarizable material, and this set of dipoles is a simple example, the polarizable material will orient itself. It will orient its dipoles so that it sets up an internal field that tends to cancel out the applied field. And that's why epsilon is always greater than 1, because the field here is less than the field that we would have if this charge density were present and we just had free space. That's because part of the field that would be there in free space is canceled out by the orientation of these dipoles. Well, there are different sources of these dipoles, and one of the interesting features of those is that they have, do I have a plot here? No, I guess not. One of the interesting features of those is that they have different time constants. So if you have, for example, an alternating current, the dielectric constant value will be a function of the frequency with which you reverse the electric current, because the dielectric constant requires the alignment of dipoles, and depending on the dipoles, what the dipoles are, it's more or less difficult for them to align. The porous materials with large pores have some of the biggest dielectric constants and also the slowest time response. In that case, if you imagine a pore, charges can accumulate on the surfaces of the pore. So I will divide positive and negative charges across the hole in the material. Well, that can make a big contribution to the dielectric constant if the pore is big enough, but it's going to take time for that reorganization to occur in an insulator, so that's a big response, but slow response. Molecular dipoles can also have a very big contribution to the dielectric constant, but again, a somewhat slow response. Imagine you have big polar molecules sitting in a fluid. You put on an electric field, those polar molecules will align to oppose the electric field, giving you a big dielectric constant. However, if these are molecules of significant size, it takes some time for them to align, so the response time here is slower. Where you see these things used, because of the big values of the dielectric constant they can produce, is in capacitors that are used for energy storage. These great big barrels you may see in PG&E yards. They're electric, they're filled with liquids that have large polar molecules that line up, big dielectric constants. You can store a lot of energy in those kinds of devices. Ionic displacements. In any ionic material, you have positive ions and negative ions. If you put on an electric field, the negative ions can be displaced toward the positive plate, the positive ions toward the negative plate. The net effect is a dipole moment here in the middle, a field opposing the applied field, and therefore a contribution to the dielectric constant. This is an important factor because most of the insulators we use on a day-to-day basis are ionic, or many of them are. It's a smaller dielectric constant usually than the molecular displacements, but the time constant here can be very fast. It's to the order of the vibration speed of an optical phonon. Finally, the atomic dipole. Even atoms contribute to the dipole moment. And the reason is that in an atom we have a positively charged nucleus and a negatively charged electron charge around it. In the presence of an electric field, there can be a displacement of the electric charge with respect to the nucleus. And therefore, even an inert gas will have a measurable dielectric constant because of this internal polarization. This can be a very fast response. It can happen at the plasmon frequency, which is the frequency at which electrons, effective frequency at which electrons rotate around atoms. So these different effects, different physical sources of the dielectric constant also have different time constants, different response functions for themselves. What can you do with a dielectric constant? Well, if we have a dielectric constant for a given charge, increasing the dielectric constant decreases the field. There are no really important applications of that that impinge on material science. Electrical engineers do use it occasionally. The ones that do increase on material science are the fact that for a given voltage drop, which is the more common situation, increasing the dielectric constant increases the charge. Energy stored in a capacitor increases with the dielectric constant. That's why these big energy storage capacitors are often liquids, polar liquids that contain polar molecules, because they can give you a big dielectric constant and therefore big energy storage. Energy storage goes like the square of the electric field. Induced charge between adjacent conductors increases with E. Well, now that cuts both ways. If you're talking about field effect transistors, you want to maximize the induced charge because you want to bend the bands, as we described. So there you want a big E, big dielectric constant. If you're talking about microelectronic packaging, you want the conducting lines not to talk to each other. So there you want a very low dielectric constant. Both of these are major objectives in modern microelectronics. Ultra-low dielectric constants. In packaging, they're usually called low K materials. Electrical engineers tend to use kappa for the dielectric constant. Physicists use epsilon. Low K means low kappa. So anyway, that's what they're called. And you'll see whole conferences on low K materials going on around the world constantly. Critical for applications in electronic packaging. How do you get the dielectric constant down? Well, you want to absolutely minimize the polarization of the material. Two things. You want nonpolar molecules, and you want as few of them as possible, because even atoms do polarize and give rise to a dielectric constant. So for materials design, the low K materials tend to be organics based on nonpolar molecules, and many of them use a dense array of nanopores. Now, I told you if you have a big pore, and that contributes to the dielectric constant because space charge is across the pore. But if the pore is really tiny, if it's a nanopore, you don't get a space charge. So the nanopore is just free space. So basically, this is a way of making a material which is largely free space, very few molecules. If the molecules are also nonpolar, then you have something that has a very low dielectric constant. Well, of course, in the extreme case, you just use a vacuum. The problem that you face, the engineering problem that bedevils the industry and creates lots of jobs for people to do thinking, is that when you make a microelectronic device, your insulator must support the device. The wires must be separated and held in position. And if you were to replace the dielectric with a vacuum, the wires would fall in and touch each other. So you have to accomplish all of this to get low dielectric constant while still keeping enough mechanical integrity to keep your device functional and operating. And that can be a real challenge that involves mechanical engineering as well as these materials issues. High dielectric constant. What can we do to take a simple crystalline material and get the dielectric constant sky high? And if we're talking about things like the oxides in field effect transistors, the dielectric has to be very, very thin. We can't use big polar molecules. We've got to find a way to get high dielectric constant basically out of a crystal. The simple way in which that is done is to make use of ferroelectricity. Things like barium titanate, many others. We talked about that earlier. If I take barium titanate and put its crystal structure, forget the oxygens and focus only on the barium and the titanium, I have a cesium chloride structure, BCC basically, with barium here in the center and titanium in the corners. And the oxygens are distributed around here. As long as the symmetry of the cesium chloride structure is maintained, the dielectric constant is zero because the charges are all in balance. But if for some reason I get a displacement of the central barium atom with respect to the titanium and the oxygen shell, then I create a dipole moment. And it turns out that in a number of these ionic materials, barium titanate is a classic example, at low temperature, below Curie point, I get a displacive ordering in which the atoms here in the center of the crystal become slightly displaced. Not only do they become slightly displaced, they become slightly displaced in a cooperative way, so that all of the atoms in a region of the crystal will give me the same displacement. Well, each of those little displacements contributes a dipole. Adding them all up, I can get a rather healthy dipole moment, and therefore a rather high dielectric constant from these ferroelectric materials by just cooling them to below the ordering temperature of the Curie point. And this is a plot of what the polarization looks like as a function of temperature. Once the displacement happens, the polarization starts building up and saturates, and these ferroelectric materials are the things that are constant sources of excitement among people who design field effect transistors, because this is a good way to get a very high dielectric constant in a very small material. Okay, that finishes up what I want to say about insulators. On Friday, we shall start talking about the optical properties of materials.